Hello everyone, myself Om Patil and I am here with my friend Himanshu Patil. Today we are going to explain the construction and the workings of wattmeter and energy meter. Without further ado, let's get started. Firstly, we are going to take a deeper look at the wattmeter and understand its construction and working. Let's first understand what is a wattmeter and what is its purpose. A wattmeter measures electric power of a given electric apparatus or circuit. There are three types of wattmeters. Electrodynamometer wattmeter, which is used to measure both the DC and AC power. The second one, induction wattmeter, which is used to measure AC power only. And the third one, the electrostatic type wattmeter, which is used to measure AC power of a circuit with very low power factor. In this video, we'll only be taking a look at the electric dynamometer wattmeter. Now, let's have a look at the working principle of the electrodynamometer wattmeter. As previously discussed, the electrodynamic wattmeter can be used to measure both AC and DC power. It works on the dynamometer principle, which states that between any two current carrying conductors or coils, there always exists a mechanical force. We will have a deeper look into this when we take a look at its working. Now let's move on to the construction of the electrodynamometer wattmeter. When a dynamometer instrument is used as a wattmeter, the fixed coils are connected in series with the load and carry the load current I1, while the moving coil is connected across the load through a series multiplier R and carries a current I2 proportional to the load voltage as shown in the figure. In the figure, we can clearly see that the fixed coils are connected in series and there's a current I1 moving through it. When this current I1 reaches this junction, it gets proportionally divided into two parts, one which goes through this multiplier and another which goes through the load. Now let's see how the electrodynamic wattmeter is shown in a circuit. This fixed coil is shown as a current coil and this movable coil is shown as a potential coil. At the potential coil there is a pointer attached which shows the readings just as in this diagram. Now let's have a look at the working of the electrodynamo wattmeter. When the wattmeter is connected in the circuit to measure the power, the current coil carries load current and potential coil carries current proportional to the load voltage. Due to the currents in the coil, there exists a mechanical force between them. As the current moves through the fixed coil produces an electromagnetic field which then induces a torque on the movable coil and moves the pointer over the scale. Now let's have a look at the merits and demerits of dynamometer type wattmeter. Merits. First, they can be used as a measurement of AC as well as DC power. Second, they have a uniform scale. Third, they have high accuracy if designed carefully. Fourth, they don't have hysteresis errors. Fifth, they have low power consumptions. And last, light in weight. Now, moving on to the demerits. At low power factor, the impedance of potential coil causes serious errors. Now, in this case, instead of using the electrodynamo wattmeter, we can use the third type of wattmeter which we saw at the beginning of the video, which is electrostatic wattmeter. Second, the reading of the instrument may be affected by strong magnetic fields, and in order to prevent it, the instrument is shielded by enclosing it in a soft iron case. Third, they are much more expensive than other types of instruments. Fourth, these instruments are sensitive to overloads and mechanical impacts, therefore care must be taken while handling them. And the last, the operating current of these instruments is large due to the fact that they have weak magnetic field. Finally, we'll be looking at the calibration of wattmeter. The method we are using is the comparison method using a standard meter. We will be connecting a lamp load across both the standard meter and the wattmeter which we want to calibrate. Since the load is the same, the wattmeter reading should also be same. We can calculate the percentage error by this method. That's it from me. Now, Himanshu Patil will take over and explain you the construction and operation of energy meter.
Hi everyone, my name is Himanshu Patel. Today I explain you the concept of energy meter. So Om already explained you the concept of watt meter. So let's start with the energy meter. Energy meter is an instrument used to measure the energy consumed in the given circuit. And electrical energy can also express in kilowatt hour or kilowatt hour, and thus 1 kilowatt hour is equal to 1 unit of energy. Let's see the types of energy meter. First one is the electrolytic energy meter. Second is a motor meters. There are three types in the motor meter: mercury motor meter, commutator meters, induction energy meter. And there are also three subtypes of induction energy meters. First one is a one phase meter, second one is a two phase, and third one is a three phase. Let's see the third type of energy meter: clock meter. Fourth one is a electronic energy meter. Let's start with the single phase induction type energy meter. One-phase induction watt-hours meters are extensively used to measurement of electrical energy in AC circuits. An induction watt meter is essentially an induction watt meter with control spring pointer, removable brake magnet, and counting mechanism is provided. You can see this is the construction figure of the single phase electrical meter. There is a recording mechanism, supply voltage is provided, load, braking magnet, series magnet, shunt magnet, and the spindle. So let's see what how these parts are working. Let's see the principle of the energy meter. The basic principle of induction type energy meter is electromagnetic induction. When alternating current flown through the two suitably located coils produce rotating magnetic field, which is caught by the metallic disc. Suspended near to the coils, thus EMF induced in the disc, which is circulates eddy current in it. By interaction of rotating magnetic field and eddy current, torque is developed and cause the disc to rotate. So let's see the construction of energy meter. In an induction type single phase energy meter as shown in figure as following map. First one is a driving system, second one is a moving system, third one is braking system, and fourth one is recording mechanism. Let's start the driving system. It consists of two electromagnets. First one is the shunt magnet, second one is the series magnet. Let's see series magnet. It consists of number of U-shaped laminates of silicon steel together to form a pose. A coil of thick wire having a few turns is wounded in both legs of U-shaped magnet, and the coil is known as current coil, which is connected in series with load. Produce a magnetic field proportional and in phase with line current. Let's see what is the shunt magnet. It consists of number of M-shaped laminations of silicon steel assembled together to form a coil. The coil of thin wire having large number of turns involved on central limb of the magnet. This coil is connected across the load. Thus, it is excited by current proportional to the supply voltage and known as potential coil. So let's see second type of system, that is moving system. Moving system is essentially consists of light rotating aluminum discs mounted on vertical spindle or shaft. The shaft that supports the aluminum disc is connected by the gear arrangement to the clock mechanism on the front of the meter to provide information that energy consumed by the load. The time varying fluxes produced by shunt and series magnet induce eddies current in the aluminum disc. The interaction between these two magnetic fields and eddy currents set up a driving torque in the disc. The number of rotation of the disc is therefore proportional to the energy consumed by the load in a certain time interval and is commonly measured in kilowatts hour. So let us see the third type of system, braking system. Damping of the disc is provided by a small permanent magnet located diametrically opposite to the AC magnet. This disc passes between the magnet gaps. The movement of rotating disc is through the magnetic field crossing the air gap, set up eddy current in the disc that react with the magnetic field and exerts a braking torque. By changing the position of the brake magnet or driver tick some of the flux therefrom the speed of rotating discs can be controlled. What is the recording mechanism? Let's see what is recording mechanism. The function of recording or registering mechanism is to record continuously number on the die which is proportional to the revolution made during the moving system. The number of revolution on the disc is a measure the electrical energy passing through the meter. So let's see what is the operation of that parts or the systems. When the energy meter is connected in circuit, the current coil carries a load current and pressure coil carries the current proportional to the supply voltage. The magnetic field produced by in series magnet in phase with the line current and magnetic field produced by the shunt magnet is a quadrature with the applied voltage. Thus, a phase difference exists between the fluxes produced by the two coils. This set up rotating magnetic field which interacts with disc and produce a driving torque and thus disc start rotating. The number of revolutions made by the disc depend upon energy passing through the meter. The spindle gear to the recording mechanism so that energy consumed in the circuit is directly registered in kilowatt hour. The speed of the disc is adjusted by adjusting the position of braking magnet. Example, if the energy meter registers less energy than the energy actual consumed in the circuit, then the speed of this has to be increased, which is obtained by shifting the braking magnet near to the center of the disc and vice versa. When induction wattmeter is connected in the circuit to measure the energy, the shunt carries current proportional to the supply voltage and the series magnet carries the load current. Therefore, driving torque is directly proportional to the flux due to voltage, flux due to current and angle between them. So, driving torque is directly proportional to the VI sine 90 minus their phase angle. So, you know the 90 minus theta is the cos theta. That's why VI cos flux, VI gross phase. And therefore the torque, there is a VI gross phase means the power. Therefore the torque is directly proportional to the power. The braking torque is due to eddy currents induced in the aluminum disc. Since the magnitude of eddy current is proportional to the disc speed, the braking torque will also be proportional to the disc speed. See the braking torque. For steady speed of rotation, Td equal to Tb. Power is directly proportional to the number of revolution. So multiply both side by T, we get the power multiplied by D is directly proportional to the number of revolution into time. So power into time is energy. So energy is directly proportional to the number of turns in time T. So the conducting mechanism is so arranged that the meter indicates directly and not the revolution. Directly indicates the kilowatt hour energy, not the revolutions. So let's see what is the next one. What is the meter constant? N is energy. N is equal to K is the meter. N is equal to K energy. Therefore, K is the meter constant. So K is equal meter constant is equal to number of revolution divided by energy. That is number of revolution divided by kilowatt per hour. This is the number of revolution means by the disc for 1 kilowatt of energy consumption is called meter constant. Thanks. This is the explanation of energy meter.